Okay, welcome back to the deep dive. Today, we're really getting into the weeds, technically speaking. We're looking at the state of advanced LLMs.
Yeah, drawing a lot from some recent conversations with Kimi's founder.
Right. And our mission, as always, is pretty specific. If you're involved in development, maybe architecture, or planning those big enterprise deployments.
They're cutting through the hype. We want to pull out the actual technical mechanisms they're using to engineer for, real scale and agency.
Exactly. We're moving past just benchmark scores and looking at the strategic engineering.
Yeah.
How do you build systems that can handle complex, multi-step tasks over hours, not just seconds?
And the core idea we picked up from the source material, this sort of intellectual frame, is thinking about AI development like climbing an infinite mountain.
Hmm.
Every time you solve a problem, reach a new ridge, it just reveals a harder, more complex problem up ahead. It's kind of a beginning of infinity vibe.
Yeah, I like that framing because it means the goal isn't some fixed summit, right? It's about constantly increasing the rate at which you can climb, how fast you can tackle the unknown.
Exactly. And the technical goal then becomes using AI itself as a kind of magnifier for human effort to climb faster.
Which you can really see in the big shifts over the past, 18 months
Yeah,
or so.
absolutely. The early days were all about massive pre-training, then maybe some SFT, supervised fine-tuning,
Standard stuff.
standard stuff. But the 2024-2025 landscape is, well, it's intense. Now it's pre-training plus really advanced reinforcement learning, RL, and these much more sophisticated agentic systems.
So the complexity has shifted more towards post-training, alignment, and making it actually do stuff.
That's where a lot of the really hard engineering challenges are now, yeah.
Okay, let's dive right into that. How does this complexity show up at inference time? We need models doing more than just answering a quick question.
Right. Which brings us to this concept of test time scaling.
Test time scaling. So
Yeah.
scaling how many tokens you use during the prediction or inference phase.
Exactly. It's about getting past the limitations of older models that were basically tuned for one good answer, one dialogue turn.
Okay.
Test time scaling is the technical way to let the model, well, think longer, to reevaluate, plan, execute over maybe hundreds or thousands of steps and tokens, all within that single inference run.
And that's how you unlock these complex multi-hour tasks.
It's the foundation for it.
Yeah.
And the sources really break this down into two main ways, two sort of distinct mechanisms for getting that sophistication.
Okay, mechanism one, this is the internal approach, the brain in a vat.
Yeah, the brain in a vat. This is all about boosting the model's reasoning power, but without it talking to the outside world.
Purely internal thought.
Purely internal. It uses advanced RL stuff, like strong self-reflection, maybe inner monologue loops. The model basically tries to solve the problem multiple times inside its own context window.
So it generates a guess, critiques its own guess, maybe throws it out, tries again.
Precisely. It generates a hypothesis, checks it, refines it, generates a better one. It's not just spitting out the first answer it thinks of.
So instead of just one answer, it's like generating 10 potential answers and running its own little validation process on them.
That's a good way to put it. Technically, it's about improving its P at K capability.
Probability at K samples.
Right. The chance of getting the right answer if you let it try K times internally. The goal is to make that so good it effectively becomes P at 1. The single best output it produces is very likely correct.
Okay.
And there's a fascinating technical detail here from the research they mentioned. It seems like sequential reasoning, where the model builds on its previous internal attempt step by step.
Like serial processing.
Yeah, serial sampling and reasoning.
Yeah.
That might actually have a higher technical ceiling, lead to better results, than just generating K samples all at once in parallel.
Huh. That sort of self-correction loop seems powerful.
It seems to be, yeah.
Okay, so that's the isolated brain. Mechanism two is the complete opposite. Agentic interaction.
Right. If the first one is thinking really hard in silence, the agent is thinking while interacting with the world.
It's fundamentally operational then.
Absolutely. It's an operational sequence. The model doesn't just think, it acts. It uses external tools. Could be a search engine, a web browser, maybe running some code.
And the key difference from just, sticking a tool use API on a model.
The key is that the environment changes based on the model's actions, and the model gets feedback from that change.
Ah.
So the code runs and throws an error, or the search results give it new information. That feedback updates the agent's internal state, its understanding of the task, and informs its next action. It's a proper planning and execution loop.
Right. It's reacting and adapting based on external input.
Exactly.
Okay, perfect place to pause. Let's bring in our technical assessment, neural signal check. So if you're out there developing or deploying these models, why is this distinction critical? Brain in a vat versus agentic interaction. What does it actually mean for what you can achieve operationally?
Well, it's really the difference between having a, let's say, incredibly smart predictor, like a brilliant consultant.
Versus an autonomous worker.
Exactly. Versus a truly autonomous engineer or analyst. This test time scaling, whether through internal reasoning or external action, or maybe both. It's the absolute foundation for any kind of autonomous enterprise deployment. You just can't skip it.
And the example they gave was pretty complex.
Yeah, the source mentioned a task like clone a code repository, translate it to a completely different programming language, debug the translated code, write tests for it, ensure it actually runs smoothly, maybe across several code commits.
That's not a 5-minute job for a human.
Not at all. Hours, maybe days. To get an AI to do that autonomously without constant human oversight, it has to be able to scale its own thinking and action process over potentially hours, using a massive number of tokens, managing the state of the task.
You need that test time scaling capability.
You absolutely need it. No way around it for that level of operational independence.
Okay, speaking of scaling and limits, let's pivot. Because there's this huge challenge looming over everyone building foundation models right now. The data bottleneck.
Ah, yes, the strategic limiter. Scaling laws tell us pretty clearly that more intelligence generally requires more data.
What?
But the problem is the rate at which we're generating truly high-quality training data, the kind of data that actually provides novel information and drives cognitive gains, that rate is slowing down. It's not keeping pace.
So compute might be getting cheaper, relatively speaking.
Yeah, compute is less of a constraint than it used to be. But the amount of top-tier data feels like it's hitting a kind of ceiling. It's becoming a constant, not an exponentially growing resource.
Which means you can't just solve problems by throwing more GPUs at bigger models if the data quality isn't there. The learning flattens out.
Exactly. The intelligence gain per token starts to diminish. So the whole strategic focus has had to shift.
From just compute efficiency training faster to token efficiency.
Precisely. Token efficiency. How do you maximize the intelligence gain, the learning you get from every single token you feed the model? The goal becomes, metaphorically, eating the same amount of food, but growing the brain more.
Right. Getting more bang for your data buck.
That's the core challenge. And this pressure, this constraint, is what apparently forced Kimi to reconsider something really fundamental, something most people took for granted for, like, a decade.
Which was?
The optimizer. They actually moved away from the atom optimizer.
Wait, stop. The atom optimizer. The one that's basically been the default standard for almost all deep learning for years.
The very same.
That's not just tweaking a parameter. That's like ripping out the engine and putting in something completely different. What does that signal about how hard they were pushing?
It signals they were hitting that token efficiency wall so hard they were willing to re-engineer the absolute fundamentals of the training process. They didn't just accept atom as, the final word.
What did they use instead?
They pioneered this non-atom approach based on matrix orthogonalization, MION, they call it. It apparently came from an earlier concept, something called the C term, but they developed it into a full-fledged optimizer.
And how does it work differently? What's the mechanism?
It fundamentally changes how the gradients, the learning signals, are scaled and applied during training. Instead of Atom's adaptive moments, it uses techniques related to keeping weight matrices orthogonal, which seems to lead to more stable and efficient learning, especially concerning the value extracted per token.
Okay, so the theory is interesting, but what was the actual impact, the measurable difference?
The claim is pretty significant, roughly a 2 times gain in compute optimal token efficiency.
Wow, 2x.
Yeah, which basically means for a given amount of compute budget, their model trained with MIN could learn as much from one data set as a model trained with Atom might learn from 2 similar data sets.
So it's just much better at compressing the knowledge from the data. The loss drops faster for the same data exposure.
Effectively, yes. The learning process itself is more efficient at capturing the information in those high-quality tokens. It's a direct attack on the data bottleneck by optimizing the learning mechanism itself.
A really clever way to sidestep the data ceiling, then? But breakthroughs like that rarely come without new problems, especially at scale. Did the source mention issues?
Oh, absolutely. It's a classic scaling story. MION worked great in smaller tests, but when they scaled it up for training K2, their big model, boom, new instability.
What happened?
During the massive parallel training runs, a key internal parameter they monitor, called the max logic, would apparently just explode, go haywire.
Okay, for listeners maybe not deep in training internals, what's max logic roughly measuring, and why is an explosion bad? Sounds bad.
It sounds bad because it is bad. Think of max logic as like a safety gauge for the numerical stability of the really large calculations happening during training, especially around the gradients. If it explodes, it means the numbers are becoming unstable, heading towards infinity, or not a number.
And the whole training run just crashes.
The whole thing collapses. Complete failure. So they had to invent new solutions right there during the K2 training, specifically novel ways to clip or limit those values on the fly.
Another example of problems you only discover when you actually try to build something huge.
Textbook example, scale reveals all the hidden flaws.
So alongside fixing the optimizer, they were also tackling the limited amount of high-quality data using augmentation, right? The rephrasing strategy.
Yeah, that was the other part of the puzzle. If you can't find new, truly high-quality data, you have to get maximum mileage out of what you've got.
But you can't just repeat the same data over and over.
Exactly. Feed the model the exact same sentence too many times, and it just memorizes it. Catastrophic overfitting. Bad for generalization.
So they use their own models to rephrase the good stuff.
Right. Use powerful models to subtly rewrite, restructure, and rephrase the existing high-quality examples. Keep the core concepts, the valuable information, but present it in slightly different ways.
Creates variety, avoids rote memorization, helps the model generalize better from that limited pool of great data.
That's the idea. Squeeze every last drop of value from those precious tokens.
Okay, so better learning mechanisms, smarter data usage.
A lot of this is ultimately aimed at building better agentic systems, right? The models that can do things.
That's a primary goal, yes.
But the source highlighted a major snag here, too. Agent generalization seems way harder, much more brittle, than just getting a model to chat nicely.
It really is. That's arguably the central technical challenge for agents right now, avoiding severe overfitting.
Overfitting to what, specifically?
To the specific tools they were trained with, the particular software environments they interacted with during training, or even the specific benchmark tasks they were optimized for.
So you train an agent to be great at using, say, tool A in environment X for task Y.
And it becomes brilliant at exactly that. But then you ask it to use tool B, or operate in environment Z, or tackle a slightly different task Y prime.
And it falls apart. It's brittle. Often, yeah. It hasn't learned the underlying skill broadly enough. It just learned the specific pattern of that one training setup. Making agents truly adaptable and robust in new, unseen situations, out of distribution or ode scenarios, is incredibly difficult.
And this difficulty, this generalization challenge, leads to basically two different philosophies or strategies for developing and deploying agents that we see in the industry.
Yeah, the sources laid out these two camps quite clearly. First, you have the reverse engineering or scaffolding approach.
Okay, what's that?
That's where you take a powerful pre-existing foundation model, like a big generic LLM, and you essentially build around it. You add external tools, you do a lot of clever prompt engineering, maybe you build some wrappers.
You're trying to coax the existing brain into using tools it wasn't necessarily trained for from the start, kind of reverse engineering its capabilities.
Exactly. You're trying to figure out how to make this general model work with your specific tools and workflows. It's flexible, definitely, and often faster to get started with.
But the source suggested it has a lower ceiling.
Potentially, yes. The argument is that because the model wasn't fundamentally trained with those specific tools and interaction patterns in mind, the integration might never be perfectly seamless or maximally efficient. The ultimate performance might be capped.
Okay, so the alternative philosophy
Is what they called first-party integration or forward design. And this seems to be the direction Kimi favors.
and this is
Here, you design the whole system more holistically from the beginning. You define the tools the agent will use, the environment it will operate in, the specific ways it will handle context and information first.
you architect the ecosystem first.
Right. And then you train the foundation model within that specific pre-designed environment. The model learns to use those first-party tools and operate in that context as a native part of its training.
That sounds like it should lead to much tighter integration, maybe higher performance. But let me push back on that. Isn't that a huge commitment? Well, if you build this perfectly integrated system, aren't you potentially locking yourself out of using maybe a better external tool that comes along later? or adapting quickly if the required environment changes drastically, it feels less flexible. That seems like a major strategic trade-off, especially for enterprise deployment where things change.
It absolutely is a critical trade-off. That's a very fair point. First-party integration is definitely more resource-intensive up front.
Yeah.
And yes, it could make pivoting to entirely different external tools harder later on.
So why do it? What's the payoff?
The argument is that the synergy you get, the deep integration between the model's internal learned weights and the specific tools and environment it was trained for, provides a fundamentally higher performance ceiling within that designed ecosystem.
Ah, okay. So it's optimized for that setup.
Exactly. Everything is designed to work together seamlessly from day one. So for an enterprise that knows its core technical stack and needs maximum reliable performance within that stack, the potential for a higher long-term performance ceiling might outweigh the reduced flexibility. It's a strategic bet.
Got it. Thinking about that long-term roadmap, the source talked about these L levels. L2 for reasoning, L3 for agentic behavior.
Right, sort of capability milestones.
And the ultimate goal, L4, was defined as innovation, where the AI, say K2, can actually help develop the next generation, K3.
Yeah, that's the holy grail, isn't it? The recursive self-improvement loop. AI helping create better AI.
To get there, you obviously need top-tier reasoning, L2, to plan complex tasks, and top-tier agent, L3, capabilities to execute them.
You need both working together. But the source suggests that even getting to reliable general L3 is being held back right now by a major bottleneck.
Which is?
Evaluation. Our methods for evaluating how good agents actually are,
Yeah.
they're just not good enough yet.
And this connects back to that overfitting problem and specifically the danger of reward hacking.
Exactly. It's the classic issue. If your benchmark tests are too narrow or too easily gamed, models learn to get a high score on the test without actually mastering the complex general skill you want them to learn.
They hack the reward function. They look good on the test, but fail in messy, real-world situations.
Precisely. They're brittle. And that's why the thinking seems to be shifting towards needing L4-style techniques, essentially using AI to help train and align AI just to create evaluation methods and benchmarks that are robust enough to measure true generalization and prevent this kind of reward hacking.
Wow. So you almost need the next level of AI just to properly measure the current level.
It seems that way, especially for complex agentic generalization. It's a really tough nut to crack.
This whole technical journey feels relentless. We started with that infinite mountain idea.
Yeah.
And you see it playing out. You solve fundamental problems like token efficiency with MION, which is huge.
Yeah.
But that just reveals the next massive challenge, making agents generalize reliably. And solving that seems to require a whole new innovation loop just to figure out if you're even succeeding. The curve stays steep.
It really does. And, this ties into probably the biggest architectural tug-of-war happening in the industry right at this moment.
Which is?
While everyone's pushing hard for these super capable reasoning and agentic models, there's this simultaneous push for massive long context LC support, models that can handle millions of tokens.
And the problem is getting both at the same time.
The problem is often in the architecture. Some of the newer architectural ideas designed specifically for huge context windows, things like certain types of linear attention mechanisms that scale more easily than standard transformers.
They sometimes achieve that length, that massive context, but at a cost.
Exactly. Sometimes they seem to damage the model's core intelligence, its raw IQ or reasoning ability. You get the long context, but the model becomes, well, dumber, less capable on complex tasks that fit within shorter context.
So the grand challenge is building an architecture that gives you both multi-million token context and the super high intelligence that comes from things like MION and advanced RL.
That's a tightrope walk. How do you scale context dramatically without cannibalizing the core cognitive capabilities you fought so hard to gain through better optimizers and alignment techniques? Solving that trade-off is, I think, the defining architectural challenge for the next generation of really powerful foundation models.
So for you, our listener, knee-deep in development or deployment planning, that really crystallizes the strategic decision point, doesn't it?
It really does.
Are you going down the path of maybe faster initial deployment, but potentially lower ceiling, the reverse engineering, scaffolding around existing models? Or do you invest the resources, take the bigger bet on that first-party integration approach, aiming for that higher ceiling of token and operational efficiency, even if it means less flexibility?
Yeah, that choice really dictates your potential long-term capability for truly autonomous deployment. You need to think hard about where your biggest bottlenecks are right now.
Is it raw compute power? Is it the quality or quantity of your data? Or is it the brittleness of your current systems when they face real-world complexity?
Because the answer to that will probably tell you which of these scaling mechanisms, which development philosophy, is most critical for your immediate technical roadmap.
Lots to think about. Until next time, keep navigating those trade-offs.